Welcome back everyone. In this lesson we are going to learn about two separate methods. Actually both of them are complementary to each other. We will learn about Gauss-Seidel method and Jacobi iteration. Both of these methods are designed to solve for simultaneous linear algebraic equations, and also they are very much suitable for computational implementations, and they are far more preferable than the Gauss elimination or Gauss-Jordan methods for computation from the perspective of computational implementation. So Gauss-Seidel method is an iterative method. So in Gauss-Seidel method, each equation is solved for an unknown variable. So if you remember, there will be some unknown variables in the system of linear equations. So each of the equations is solved for an unknown variable, and the result of that unknown variable is used for determining the next unknown variable. So it's a dynamic approach. The Gauss-Seidel method is very much similar to the method that we have covered in lesson 9, which is simple fixed point iteration. If you remember, that simple fixed point iteration in lesson 9 was used to find out the roots of equations, and we just converted the original equations into an iterative form, and at one iteration we determine an approximation of the original root. Then in the next iteration we use this value as the initial point. So that's how in this iterative approach we used the fixed point iteration. So Gauss-Seidel method is very much similar in spirit to that technique actually, but simple fixed point iterations had some limitations. Sometimes it was non-convergent, and also when it converged it often did so very slowly, so it was a very slow method. So I want to tell you that a Gauss-Seidel method also faces such kind of limitations, such kind of shortcomings in its algorithm. So we will see how this method can be implemented. So the algorithm is very straightforward. So the Gauss-Seidel algorithm states that you need to have an initial value for each of the unknown values. Remember, in Gauss-Jordan elimination or Gaussian methods, we did not need any initial values. But in Gauss-Seidel method, we need at least a initial value for each of the unknown variables. Remember, for each of the unknown variables, we need an initial value. So once we have the initial values, we can determine the approximation to each unknown value using this equation. So that means we have the initial values for each of the unknowns, and then using this formula and the initial values, we determine the next approximation values and replace the previous approximation of unknown values using the present approximations. So in this way we continue after iterations to modify our previous approximations with the present approximation from this formula. So it's an iterative approach. So how do we stop the iteration? So if you remember, the general procedure of stopping an iteration is to find out the approximate error. So convergence can be checked out in the code by this equation. That means the approximate percent relative error, which is denoted as the present value minus the previous value, or the present approximation minus the previous approximation divided by the present approximation times 100%. So that's how we calculate the approximate percent relative error, and once that approximated error is less than a predefined error, we can stop the iterations, and if not, we can go back to step 2 and recalculate the whole procedure. So that's how the algorithm works in Gauss-Seidel method. So if we try out an example, I think that would be the best to understand this algorithm. So before going into the details, let's see what does the formula in step 2 that we have said in the algorithm, the Gauss-Seidel algorithm. What does this mean actually? Here we have seen that the xi terms, that this can be used to approximate each of the unknowns. In the denominator we have aii, and in the numerator we have a large summation term. So let's say we have a system of 3 equations. The equations are denoted in this manner. Look at this, inside the box these are the three equations that we are given. So if we modify these three equations, we can easily get these three equations. From the first equation, we can determine the x1 in terms of x2 and x3. From the second equation, we determine the x2 in terms of x1 and x3. And from the third equation, we determine x3 in terms of x1 and x2. So we can easily algebraically manipulate these three equations to get these three terms, these three equations. So look at this. In the first equation, we are given the second and the third term, a12x2 plus a13x3. So and the first coefficient is a11. Okay. So if we just remove these two values, a12x2 plus a13x3 to the right hand side of the equation, then we would get b1 minus these two terms, which is something like this, and we divide this whole term with the coefficient a11, and that's how we get the x1. So that is very straightforward. Okay, that's the main algebraic manipulation. Similarly, in the second equation, we want to determine the x2 in terms of x1 and x2. That means we move the first term and the third term to the right hand side. So we will get b2 minus the first term and minus the third term, which is like this: b2 minus the first term minus the third term divided by the constant term with the x2, which is a22. Okay, so this is the equation. Next, in the third equation, we want to determine the value x3, and to determine the value x3, we need to move these two terms to the right hand side. So this would get b3 minus the first term minus the second term. So b3 minus a31x1 minus a32x2 divided by the constant coefficient, that means coefficient of the x3. So that's how we manipulate the three equations and get these three equations. Okay, so one thing to notice here, that look at this, in the x2 we need to use the value x1. So which x1 do we use? This x1 is actually the determined value from the first equation. Okay, so using the initial values, we determine the x1 from this equation, and then the determined x1 can be used in the subsequent step to find out the value of other unknown variables. So that's why in the second case, whenever we are finding out the x2, we already have determined a modified element, a modified approximation of x1 in the first case. So that's why we are going to use that modified version in our x2 equation. Since we have not already determined the modified version of x3, that's why we are going to use the initial value of x3 here. Similarly, in case of the third equation, we have already determined the value of x2 in the second case, and that's the value, modified value, that we are going to use in the third equation, and the x1 is going to be that is determined from the first equation. So using these x1 and x2, the modified elements, we can determine the value of x. Remember this, in case of determining this x, we are not using the initial values of x1 and x2 because we have already determined the modified elements, okay, the modified approximations, and that's why we are going to use the most current determined values of these unknown variables. So it's a dynamic approach. So Gauss-Seidel method is actually a dynamic approach like the Thomas algorithm. If you remember from the Thomas algorithm, once we have determined a value, modified value of any element of the original matrix, we use that value onwards on the subsequent steps. So that's how we are also using in the Gauss-Seidel method. That's the main theme we are using in the Gauss-Seidel method. So let's look at an example using the Gauss-Seidel method. Let's say we have a system of three equations, which is something like this. Okay, then we are going to use these three equations to find out the modified approximations of our Gauss-Seidel method. So initially, let's say we are given the true solutions, which are x1 equal to 3, x2 equal to minus 2.5, and x3 equal to 7. So we are given the original true solutions. We need to find out the values from the Gauss-Seidel method and compare those with these true solutions. So let's see how we can do that. So we convert these three equations algebraically to find out these three terms, these three equations. From the first equation, we determine x1 in terms of x2 and x3. From the second equation, we determine x2 in terms of x1 and x3. And from the third equation, we determine x3 in terms of x1 and x2. Okay. So in the first iteration, what we are going to use, we first assume that the initial values of all the unknown values are variables are 0. So if we are not given the initial values, we are going to assume that all of the initial values are 0. But if we are given the initial values, then there is no need to assuming that they are zeros. So in the first iteration, using these initial values, we determine the x1. And in case of determining x1, we are just using the initial values of x2 and x3, which are 0. That's why these two terms are zeros. So we have determined the x1. But in case of determining the x2, we already have determined a modified approximation of x1, which is 2.616667. So this modified approximation is going to be used in the second iteration. But since we have not yet determined any x3 term, that's why we are going to use the initial value, which is 0. So that's how we use the x1 to determine the value of x2. And in the last case, we are determining the value of x3. But since we have already determined the values of x1 and x2, so that's why we are going to use those values here to determine the value of x3. So after the first iteration, the modified approximation of the original values, unknown values, are x1 is equal to 2.616667, x2 is also determined in this manner, and x3 is also determined in this manner. So using these three values, we are going to assume that these three values are going to be the initial values for the next iteration. So in the second iteration, we have the initial values, something like this. These are the values that has been determined from the first iteration. So for the second iteration, these are going to be the initial values. Okay. So using these initial values, we can easily determine in the same manner x1, x2, and x3. Since for determining x1, we are not given the we are not yet calculated the x2 and x3 terms. That's why we are going to use the initial approximations for the second iterations. That means x2 is going to be used here and x3 is going to be used here. But in case of determining the x2, we have already determined the x1 term. That's why we are going to use the modified version, not this initial approximation, because we have already determined the modified version. So that's why we are going to use the most current approximation, which is this one. And for the x3 term, since we have not determined yet any of the x3 term yet, that's why we are going to use these initial approximation. Okay, so that's how we are going to find out the x2 value. And finally, if we want to find out the value of x3, we are going to use the most current x1 and x2 to determine the value of x3. So once we have determined the values, approximated values for x1, x2, and x3, we are going to find out the errors. Okay, so the errors are necessary to stop the iterations. So since we are given the true solutions, that's why we are going to determine the errors, true errors. That means epsilon t. This is the true percent relative error. But if we were not given the true values, we would have used epsilon a terms. That means the approximate percent relative errors. So that's the difference. So if we compare with the true values and our determined values from the second iteration, we will get these errors. 0. For epsilon t1, that means for the x1 terms, the error is 0.31%. For the x2 term, the error is 0.015%, and for the x3 term, this is the error. So that's how we are going to use the errors. So once we have determined the errors, so we can easily consider the criteria to whether to stop the iterations or go back to the calculations. So that was the traditional Gauss-Seidel method. Now we are going to see another version of the Gauss-Seidel method, which is the Jacobi iteration. So if you remember, in the Gauss-Seidel method, we were just whenever we are calculating the values of x1, x2 and x3, we were using the most current approximation of the unknown variables. Okay, so if we have a most current approximation using the equations, we no longer use the initial approximation, rather we use the most current approximated one. That's what we have seen in the Gauss-Seidel method. But in Jacobi iteration, we wait for entire iteration. For example, whenever we are using the x1, x2 and x3 terms in the equations, we in Jacobi method we always use the initial approximations. Okay, so Gauss-Seidel method is a dynamic method, but Jacobi iteration is, of course, it's a dynamic method, but we wait for an entire iteration to use the modified version of the approximated solutions. So that's the difference between the Jacobi iteration and the Gauss-Seidel method. So if you see in this figure, on the left hand side we are using the Gauss-Seidel method, and on the right hand side we are showing the Jacobi iteration method. So the formulas are going to be the same, but the difference comes where to use the x1, x2 and x3. For example, in the Gauss-Seidel method, look at this. Whenever in the first case we have determined the value of x1, and in the second equation we are just going to use the most current x1 term. That means we are no longer using the initial approximation, rather we are using the most current approximated value of the unknown variable. Similarly, when we are determining the x3, we are using the x2 and the modified x1 terms. So that's the difference. So that's the case where we are using the Gauss-Seidel method. We are using the most recent version of the approximated values. Okay, but let's see what happens in the Jacobi method on the right hand side. In the right hand side, let's say in the first iteration we are using the same formulas. The formulas are same, but whenever we are calculating the x2, we are no longer using this most current x1 term. We are no longer using this. Rather, we are using the initial approximations. So in all of these equations, we are just using the initial approximations and get the modified approximation for the first iteration. And then using these three values from the first iteration, we are using these as the initial approximation for the second iteration. Okay, for the second iteration we are just using these three values. So in the second iteration, similarly, throughout all of these equations we are just using these three values. Okay, we no longer using the most current one. That means this x1 is no longer using in this place. This is not happening in Jacobi iteration. So that's the difference between the Jacobi iteration and the Gauss-Seidel method. So in this lesson we have seen the basics of Gauss-Seidel method and also the difference between the Gauss-Seidel and the Jacobi iterations. In the Jacobi iterations, we wait for an entire iteration to use the entire set of new approximated values, but in Gauss-Seidel method we no longer wait. As soon as we have a modified version of the approximated unknown value, we start using that value onward. So I hope you understand the difference between these two methods. So Gauss-Seidel methods and Jacobi iteration both are very much suitable for computational purpose. So please try out the MATLAB course that I have attached with this lesson for Gauss-Seidel method and Jacobi method. And with this lesson, our discussion of linear system ends here. We have learned about the Gauss-Jordan method, the Gaussian elimination method, the naive one, and the completed one. We have seen how pivoting can solve some of the errors of Gaussian elimination, and we have seen that Jacobi iteration and Gauss-Seidel method, both are actually the same methods, but the usage of the updated values of the unknown values, that's the difference between the Gauss-Seidel and Jacobi method. We have also learned about tri-diagonal system, and we have seen how the Thomas algorithm can be used to solve such a tri-diagonal system, and we have known that tri-diagonal systems are very much common in engineering fields. For example, in quantum mechanics, whenever you are solving for non time independent Schrodinger equations, or also in computational fluid dynamics. So these are some of the examples of tri-diagonal systems. So I hope you already know all of these methods from these lectures. I hope you have learned some of the basics of these methods, and I hope you have done all the calculations and examples in these lessons that I have shown. So please go through the details of these examples and try to do those in your notebook by your hand. So those are your homeworks. So our lesson for linear system of equation ends here, and from the next lesson we are going to start our new segment. So till then, thank you so much.